Okay, welcome back, everybody. Welcome to the last two sessions. So we have one more session on optimization, routing, and IP, and then a last session on security. Both of the sessions have 4 talks each, and they'll be 1 hour each. So, yes. So we're wrapping up the poster session now. So if you have any remaining conversations, please take them to the hallway. So we need to get started. Yeah, we need to get started on the last session here. So everyone discussing near the posters, if you want to keep talking, please take your discussion to the hallway so we can get started on the last session. Okay, so the first speaker is going to be Remy Hendricks. So Remy will be talking about locating and enumerating Anycast, a comparison of 2 approaches. And he's coming from the University of Twente.
All right. Hello, everyone. My name is Remy Hendricks. I'm from the University of Twente, and I will present this paper that we did in collaboration with the Technical University of Munich and CADA. So first, some background. What is Anycast? I'm sure most of you know. So Anycast is the geographical distribution of internet services by announcing an IP address at multiple locations. It's widely used as it provides resilience and it reduces latency. And some examples include content delivery networks like Google, Amazon, but also critical internet infrastructure, so your public DNS resolvers, CCTLDs, and the root letters. So to give an example, this is Cloudflare's network, and at all of their locations, they announce Quad 1, which is their public DNS resolver, and then based on where you are in the world, you will reach the closest Quad 1 resolver. So if you query it from here, you will end up at their location in Madrid. But if you query it from, for example, New Zealand, you will end up in their location in Auckland. So the reason that these large content delivery networks and that the DNS uses Anycast is that it provides distribution and resilience to their service. So if an Anycast site goes offline, then there's another one that takes over and you still get your DNS queries resolved. So it also provides low latencies for the CDNs and reliability. And it also provides mitigation against DDoS attacks, including DDoS protection services that actively deploy it. But the problem is that Anycast is opaque. So if you connect to an Anycast IP, or if you connect to an IP address, you do not know if it is Anycasted or unicast. And that's why you need a census. And knowing what is and what is not Anycast and where it is located is useful for example, making better traffic engineering decisions, troubleshooting network problems, resilience assessment of third parties. For example, I want to know where this CCTLD is announcing their DNS, and also assessing the location of services to make sure it is, for example, GDPR compliant, and that you do not send traffic to an Anycast address that's also outside your legal boundaries. So the current state of the art in Anycast geolocation is Manycast.net, where you can query an IP address and see if it's Anycast, and then it provides you with the locations it finds. But this state of the art uses iGreedy to geolocate Anycast, which basically sends out ping measurements from multiple locations, and then it draws a circle on the maximum distance traveled by that ping packet based on the speed of light in fiber optics. And in this example, you see 4 circles. They do not overlap, and that is because this is an Anycast IP in this example, and the algorithm detects that there's a speed of light violation, and then it looks at the minimum set of overlapping circles. So the purple and the greens, they overlap. in separate locations, and then it infers the location of the Anycast sites to be in the largest metropolitan area of those regions. In this example, Las Vegas and Atlanta. But the problem with this approach is that latency measurements are known to be noisy. You have queuing delays, propagation delays in networks that will artificially inflate the maximum distance traveled. And it's also known to suffer with Anycast sites in near proximity. So for example, if you have a Cloudflare who has an Anycast site both in Belgium, in Brussels, and in Amsterdam, because they're so close together geographically, this methodology it's very difficult to distinguish between them, and it will likely find one location. So what we did is we looked at traceroute, which lets you measure the path that an internet packet takes to reach its destination, and to see if we can use this to improve Anycast geolocation, as it has been done in unicast geolocation to achieve the same goal, and it's very useful there. And for this, we used latency neighbors, which is related work from the unicast geolocation. And basically, what it does is it finds so-called latency neighbors near the destination. In our case, it's the Anycast destination. And there's a certain thresholds within how much milliseconds they must be from the destination and from the vantage point which originated the trace route. And then you geolocate these hops near the destination, and you infer the Anycast destination to be near those latency neighbors. There's more detail in the paper, but there's due to time I will move on. So to assess the performance of this methodology, we ran a large measurement campaign. We made use of KDA's ARC platform. And at the time of measurement, they had 274 vantage points inside 66 countries and 178 unique ASs. And as targets, we used Anycast prefixes from the Manycast.net census, which are roughly 14,000. And in total, we collected 3.4 million completed trace routes. And we compare our approach with iGreedy, the state of the art, by running this approach from the same vantage points. So first, is it more accurate? To assess whether it's more accurate, we make use of the root letters where there's ground truth available, so we know where they're located. And the root letters also give us a large variety in various Anycast deployments, both in size and distribution. So it covers a lot of different types of Anycast deployments you might see on the internet. So these box plots show the performance in terms of enumeration. So how many of the sites does it find out of the total number of Anycast sites there really are. And TR1 means the traceroute methodology, and GCD, Great Circle Distance, is it's for the iGreedy methodology. So the main takeaways is that the traceroute technique achieves a higher enumeration, but it also suffers from overcounting. So if you look at the box plot, it exceeds 100% because for one of the root letters, it found an additional site that didn't actually exist. And we also see that traceroute has a lower mean average error, which is the box plot on the right. So it's closer to the actual location of the Anycast site, whereas the iGreedy methodology is on average farther away. So next we look at all the Anycast prefixes in the ones we measured, all the 14,000. And we compare both the iGreedy and traceroute in terms of how many points of presence does it find for each prefix. That's what the CDF shows here. And we grouped some large spikes in the graphs, which are caused by these large cloud content delivery networks, which originate a large number of Anycast prefixes. So for example, for Google Cloud, we see that the iGreedy technique finds roughly 45 points of presence for all the Google Cloud Anycast prefixes. And with traceroute, we find that there are, we are able to enumerate up to 50. So the main takeaways is that both the iGreedy and the traceroute technique have similar performance for small Anycast deployments, which is on the bottom left part of the graph. So these are the deployments smaller than, say, 30 points of presence. But for large deployments, we do see a benefit. So for example, Google Cloud, we saw that traceroute performs better. But one exception is Amazon. And looking at the traceroute results, we figured out that Amazon does tunneling inside their own network. So from the ingress point of Amazon to the replicated service in their network, if it's more than 3 milliseconds, we cannot detect it with this technique, as it requires it to be within 3 milliseconds for the latency neighborhood. Okay, I don't know what happened here. Okay. So the technique is better, but it does come at the cost, the probing cost. So we find that on average, we need to send out 10 probes to measure the path to an Anycast destination. And since we have 274 vantage points, this adds up to a lot of outgoing probes. But there are some ways that we can reduce this. So first off, each vantage point always sees the same hops to leave its own network, which we could skip, and then we go to 7 hops on average to measure. Furthermore, we can restrain the number of vantage points we use, because we only care about vantage points within 12 milliseconds of the target for the latency neighborhood method to apply. And if we combine that with the skipping the same AS hops, we come to 5.5 probes needed from 124 vantage points on average. And then you find that the probing cost is 4 times that of iGreedy. So to conclude, we find that the traceroute methodology outperforms iGreedy, both in enumeration and geolocation, but its increase in probing cost makes it unattractive as a census technique. And we also saw that it suffers from overcounting in rare cases. Future work is to run this methodology using historical traceroute datasets, which are already being collected. And we also want to detect cases of suboptimal Anycast routing, which is a client reaching a faraway Anycast site when a nearby one is available. And with traceroute, we can pinpoint where it is happening and which location it actually reached. And we release all the data and code in a paper. Thank you.
Hi, great work. This is Oliver Gasser from IP Info. I was wondering, could you go into a bit more detail of what the overcounting issue, where that comes from within the traceroute approach?
Right. So with traceroute, you capture the reply sent back by the router using ICMP TTL exceeded, and the router can configure any address they want to send back a reply. So in some cases, they use an IP address that's not actually located where the router is. We did implement steps to filter these out using RTT validation, for example, but they still occur, and that's one reason. Also, if you have an Anycast site in, for example, Amsterdam, then with traceroute, you might see the hops near Amsterdam in London and Belgium, which are geographically close. And we have to somehow group them together to know that they all belong to Amsterdam, but that's not always. There's corner cases where it goes wrong.
Makes sense. Thank you.
Thanks. Okay.
Okay, thank
Thanks.
you. All right, our next speaker is Fabian Ile. Fabian is a PhD student from the University of Tübingen. His research interests include software-defined networking, P4-based data plane programming, resilience, and time-sensitive networking. And he's going to tell us about stack management for MPLS network actions.
Yes, thanks for the introduction. As he said, I will talk about stack management for MPLS network actions. Here's a very brief agenda slide. I will first provide some background information on the MPLS network actions framework, since I guess M&A is not that well known in the community. And then I will introduce our proposed HPH preservation mechanism. So first of all, I guess you know the MPLS protocols where labels traditionally encode forwarding information. Now, in the past years or even in the past decades, extensions to MPLS have been added that also add processing information. This is done using reserved label values. For example, you can add a special label to the MPLS stack that indicates the collection of metrics during the forwarding. So it's not only forwarding information. A problem here is now that the number of those available reserved label values is limited, and also then coding of extensions is not entirely generalized. It is generalized to some point, but not entirely. This leads to the MPLS Network Action Framework, MNA, which extends MPLS with a generalized encoding for network actions and their data. And MNA is currently undergoing standardization in the MPLS working group. The new encoding in MNA is called the Network Action Substack, short NAS, which is basically a container of multiple label stack entries, LSEs, which are re-encoded as network actions. Those containers are added to the MPLS stack. You can see it here as a sample. There are multiple of those containers in the stack, and such a container is up to 17 LSEs large, so that's pretty big. Similar to IPv6 extension headers, those network actions are added by the ingress node of a path and then are processed by transit nodes on the path. So in MNA, NAS also have scopes, and those scopes indicate on which node a network action is processed. For example, we can instruct a single node on the path to process a network action by using the select scope, or we can use HBH scope NAS, which indicate network actions that are processed on every node. That's also kind of similar to IPv6 extension headers. In the protocol design, it's stated that if such a NAS is exposed to the top, meaning if the top of stack label is popped, it must also be popped. So the NAS must be removed. It must never be on the top. That's beneficial for the select scope NAS because it is only processed by one node and we can remove it from the stack afterward. But it's a bit problematic for the HBH NAS because that NAS is processed on every node. Therefore, it must be preserved during forwarding, and we cannot just remove it. So for now, we may place it deeper in the stack. Here in the example, it's close to the bottom of stack. One last important thing for the background is the readable label depth and constraints from that. The readable label depth is also introduced together with the MNA framework, and that's a hardware parameter that indicates the number of LSEs a node can parse without performance impact. So nodes in MNA have to search the MPLS stack for network actions, and those must be, of course, within the RLD. Otherwise, they cannot be parsed by nodes. And specifically to HBH scoped actions, they must be readable at every node. So within reach of every node in the RLD. And that's what we see here as a problem. There we have a limited RLD of 3 labels, and the HBH scope NAS would be placed at the bottom of stack. It's not readable by the node, so this does not work in this example. As a solution, the protocol design says that there may be placed copies of the HBH NAS in the stack, such that they are within the readable label depth of every node in the path. So in this example here, we have a copy located below the second label, which is within reach of the first node and is then removed during forwarding. Now we come to the actual mechanism. So we first performed a hardware analysis of an MNA implementation, a P4 implementation. And there we realized that with MNA, the required RLD in nodes is very large. Why is that? First of all, we have 34 LSEs for NAS from the IETF draft. That's the result of the encoding. We can't change that for now. And second is that we must parse the so-called in-between stack. So we've seen in the protocol design, the HBH NAS is located deeper in the stack. For a hardware node, that means it starts parsing at the top of stack, scans through the MPLS stack until it finds the HBH NAS and parses all the labels in between. And now the node cannot just throw those labels away. It has to store them somewhere, otherwise they would be discarded. The problem now is that those LSEs in between, they are not relevant for the current node, like that's forwarding information or even NAS for other nodes, but we still have to allocate resources in that node, and that increases the required RLD. As a solution, we could eliminate the in-between stack by placing the HBH scope NAS at the top, but that would also mean that it will be popped, and we require many copies of that. So that leads us to our contribution, the HBH preservation mechanism. So it would be better to keep the NAS at the top. That avoids parsing relevant LSEs, but we have to still preserve it. And therefore, our mechanism constrains the location of the HBH NAS to directly below the top of stack forwarding label, such that it's always within reach. And then we reorder the stack during forwarding. That means if the top label is popped, we bring one label from below the NAS to the top. This way, the NAS is not exposed, and we also never require HBH copies. In MPLS, we have many legacy nodes, and that's a problem with that mechanism because it's not compatible with brownfield networks. Like an M&A incapable node is not aware of that move operation and therefore may expose the NAS to the top without even knowing it. And also it doesn't remove the NAS because it doesn't know the NAS. And therefore the next node will drop such a packet because the NAS is at the top of stack, which is not allowed, and it's also unknown to the node. As a solution, we can instruct the preceding node of M&A incapable nodes to bring more than one label to the top, like as many labels as popped by the M&A incapable nodes. So in this network segment here, we have two M&A incapable nodes. Each pops the top of stack label. Therefore, the preceding M&A capable node brings in total 3 labels to the top, 2 that are popped by the incapable nodes and 1 for the general mechanism. And this way, for the M&A incapable nodes, the NAS will never be exposed to the top. Now, M&A nodes are required to perform the label move operation. And how can we tell a node that it should do this? Now, if only we had a framework to instruct nodes with network actions, and fortunately, we're in the MPLS network action framework. So therefore, we define the stack management network action. And that's basically an opcode that indicates the number of LSEs to move from below the NAS to the top in a network action. We already published and wrote an internet draft on the stack management network action, which I presented yesterday in the MPLS working group. This network action is added by the ingress LER to the HBH scope NAS with a parameter n equals 1 to bring one label to the top, and to a select scope NAS for the preceding node for backward compatibility. So here's a quick example with the same network segment. This time you can see that the preceding node has the HBH NAS with n equals 1, and it also has a select scope NAS which has a parameter of n equals 2. This NAS is removed, 3 labels are brought to the top, and the NAS is never exposed, not even by the M&A incapable nodes. Quick discussion. I'm not only talking about this concept, we also have a proof of concept implementation in P4 on a hardware switching ASIC on the Intel Tofino 2. There we achieved line rate processing of the stack management network operation at 400 gigabit per second per port. We tested it with the network topology from the previous example, like with this one, but it's not really dependent on the topology, since on the Tofino, if you get a program to correctly compile, it will always run at line rate. So that's not a problem. A downside is that it doesn't work on legacy hardware that only is capable of pushing, popping, or swapping like usual in MPLS. But for those nodes which are not capable of M&A anyway, we have the mechanism for backward compatibility. The effect on the required RLD is that we do not require an in-between stack anymore, which means we waste no resources for parsing irrelevant LSEs. We have no more HBH copies, which reduces the overall stack size. The minimum required RLD is now 35 plus n LSEs, where n greater than 0 is the number of LSEs that needs to be brought to the top at once. So that scales with the number of M&A incapable nodes. We need to bring at least 1 to the top. And we further can integrate nodes with a smaller RLD in M&A, since that in-between stack is not required. Quick conclusion. So we've seen that the current design of the M&A framework has a large RLD requirement that results from parsing the in-between stack to find the HBH scope NAS. As a solution, we propose the HBH preservation mechanism, which eliminates the need for an in-between stack by reorganizing the MPLS stack during forwarding. And that reorganization is achieved using a novel stack management network action, which can be added in the HBH NAS to enable the general mechanism, or which can be added with a select scope NAS to enable brownfield deployments. Also note that for this mechanism, no changes in the current M&A drafts are required. It's just applying the novel stack management action. We have a proof of concept implemented with P4 on a hardware ASIC, which operates at line rate. So we've also shown that it works. And the minimum RLD requirement is now 36 LSEs. So that's about that. thanks for your time. I'm open for questions. I guess you have to use the microphone or.
It's okay if you can't manage, you can go to the mic. But you need to go. Can you please?
Sorry, my name is Mohamed Bobo. I'm coming from Côte d'Ivoire, Ivory Coast, Africa, West Africa. My question to you, from my perspective in Africa as an academic, it was seeming to me that MPLS was becoming kind of cold, I won't say cold topic, but something less used in our network infrastructure, or if you want, in way, no longer that the right solution to use first. We think like they branded SD1, so such kind of things. So what can you add to this concern? And thank you again.
Yeah, I mean, MPLS is quite an old technology, I know. But I know also that many providers are still using MPLS and it's still used, it's efficient, but also many are transitioning to, for example, SRv6. But I guess MPLS will still be around for quite a while. And hopefully so will be the MPLS Network Action Framework.
Okay, thank you. Thank you very much. Just to
Okay. Thank you. So our third talk will be from Simone Fairlin-Reiter from Red Hat and Karlstad University. And she'll be talking about the benefits of predictable traffic in virtual switches. Case study.
It's not your slot? No. This was the previous. This was the previous one. Predict on the benefit of predictable. Sorry.
All right, so I'm presenting here on behalf of Emil. This is work that we did last year during 2024 while he was a master student at KTH Sweden. And together with my colleague at Red Hat, Elko and Marco, we supervised him looking at the benefits of predicting traffic in OVS. So the motivation here, maybe many of you are familiar with the split that we have in SDN networking between the control plane and data plane. So there is a very common term used by slow path, which is known to have become a bottleneck in these environments. With reactive flow rule installation, this becomes a problem in some environments depending on the traffic characteristics. And the environment that we are looking into here where OVS is running is OpenShift. So this is the Kubernetes provided by Red Hat, which has very different traffic profiles as you would think that a typical network running OVS has. So there are some recent studies pointing to the slow path as the bottleneck, as people have invested a lot of research and resources on accelerating the data path. But as soon as you have to install new flow rules, which is basically letting the control plane know that this flow is known, and doing the route from kernel to user space, this has become a known problem. So some related work here pointing to what I'm talking about here. So more recently, a CCOM paper talking about the slow path. In SDI, we have had some contributions also trying to apply various forms of prediction methods to figure out if we can pre-install these rules and improve at least latency. And what we proposed to Emil here was to look at different traffic traces, and if working on the prediction would bring a general benefit regardless of the traffic profile, or we would see that in some cases doing the prediction is more beneficial than others. So again, to the problem statement here, so we go a little bit more into how OVS is implemented. So the term that is very commonly used in the OVS community, or OVS Con, the conference from OVS, is app calls. This is basically when you are going to the control plane and user space to ask for ask the question if a flow data from a flow from packets that are arriving already exist or not. Cache misses, or when this flow rule doesn't exist yet, is what adds to the latency. It adds to latency and also CPU usage in the communication. And again, so we are trying to look if we could do any optimization here. This is a little bit like another beast into the picture here. So many here might be familiar with OVS as a separate thing, but we run OVS with OVN inside OpenShift to provide layer 2 and layer 3 communication in cluster networking. So this is a different environment with inherent different traffic profile. So this is basically how you would see OVN and OVS containers or components running spread around your cluster if you're running Kubernetes. So you have at the bottom at least 2 pieces of OVS running on every worker node. If you have a very large cluster or a distributed cluster, these are entities that talk very frequently with the control plane nodes, which run other entities of OVN and OVS as well. There is another term that I would like to introduce here. There is something that it's also CCOM paper, a little bit older, 2018 or 19. The term co-flow was also introduced. So we thought about maybe can we see these flows as having some common characteristics that help us predict flows that come after a so-called base flow. So co-flow is a term that appeared in the CCOM paper, saying that for a certain pattern in communication, you could think about HTTP requests. For example, a DNS resolution, a subsequent HTTP request, and if you have, for example, dynamic content, other subsequent HTTP requests that would go to a database to fetch content. So this is what they try to define as co-flows. So you would have this base flow that is the DNS resolution, or maybe the HTTP GET flow, and all other flows that are subsequent from that would be defined as flows that come after this base flow. So we try to look into this definition here and see if there is anything that we could explore in terms of co-flows for traffic prediction. The experiment setup we used here, very simplistic, so we didn't deploy a whole OpenShift cluster. We just deployed an OVS 3.3, OVN on top. This is our system under test, 2 NICs, 100 gig each, and we had a traffic generator on the other side, which we used some of the research that Marco did before with fast click and DPDK to be able to go online rate sending traffic to our OVS. There is a little bit more details here from the implementation. So we needed timestamps because we were looking at 3 metrics when we were doing the prediction or trying to infer the prediction. We looked at CPU usage, latency, and app call statistics. So for the packets that we're generating, we needed to have some timestamps there. So Emilio implemented a small XDP program so we could inject some timestamps and get these packets on the other side. But these are very detailed aspects from the work that we did. But maybe the picture is more interesting here. So where we have the ingress and the egress timestamp in the environment. For the traffic, so I said clusters have very different traffic profiles. So we have a very frequent and very small lots of HTTP requests coming into these environments. So we have a very hard time trying to characterize if we can, for example, generalize a type of cluster traffic that runs in a customer in the entertaining business from other customer from Red Hat that is in a completely different business. We know that the characteristics are very different. The traffic is usually very, I would say, ephemeral. It's very short, short-living connections. For the co-flow workloads that I mentioned before, this definition of co-flow, we found 2 data sets, also published as part of the paper. One having very short-lived connections. This is from MapReduce and Google Search RPCs. And we have one that is more long-lived from Facebook Hadoop. Some characteristics from the traffic here, but we just wanted to test if we've any sort of extreme, very short or very long connections, we would have more or less benefits with predicting traffic. And we loaded different rates of the traffic into the cache and tried to test. So we had a perfect situation here with 1 where we know everything. Another extreme is the baseline. We don't know anything, no preloading, and some values in between to test, basically how far we get. I said this already. So the first metric I said, we looked at latency, so the mean packet latency. So we can see here on the x-axis, this is where we are testing different co-flowness or the co-flow ratio levels. And we can see that the benefits with long-lived connections are much more prominent, at least from, I would say already from 25% preloading. you can have already some benefits with long-lived connections, whereas with the short-living connections, this is much later. This is happening only when you know at least 3/4 of the traffic that goes into in your cluster. For the CPU utilization, well, no big surprises here, but the more you know about the traffic that is going, the less up calls you are doing. So the CPU load also decreases with an increasing ratio of the preloading in the cache. So yeah, these are here some very high level results. We have more results in the paper, but the time here was really short. Basically, we saw benefits in working with high long flows, long-lived flows. The high flow rates, we also worked with the rates in the test bed that we had. As you remember, I had 100 gig NICs, but we didn't go 100 gig all the time. So if you have an increasing rate of flows that show up to be basically asked, does this flow exist or not? This is also when the caching shows its benefits. And there is one thing that was implemented in OVS, so Elco is driving that upstreaming. This is the batch up calls. So basically what you're doing is waiting a little bit longer and going to user space with a bunch of requests instead of just one. Saves you CPU, but that's latency to that. That's no big news, but you have to go slow upstreaming as well. Yeah, so some future work here, things that we are trying to do with a new student is to have some prediction. Actually here, as you saw, I didn't develop any prediction model. I just show that there is a benefit in doing some prediction. Maybe we could do also hardware acceleration in the slow path in OVS, as it has been done for the data plane, at least very extensively. And we would like to do also the same sort of exercise in a larger environment with OpenShift, because we tested with a single node here, but usually you have a large environment. And OVS has also, they have also implemented a few things since this work was developed with spreading the cache across several nodes. So the nodes they do the requests locally. They try to find out locally if the flow exists instead of going all the time back to the control plane nodes. And yeah, these are the conclusions. So basically what I said before from long flows, for long flows, you see already clearly benefits in prediction with 20% preloading in the cache. The benefits are going to largely depend on the flow sizes and also the burstness of these flows. And one thing that we need to do here is also understand better the characteristics of the traffic in these clustered environments. For someone here running or working with Kubernetes platforms, this is something that we're very interested in. And yeah, thanks for listening and questions. Great, bye.
We have time for maybe one question. Okay, then maybe you can grab Simone offline. Okay, last talk for this session is Echo Chen. So Echo has over 2 decades of experience in the internet infrastructure and security field. He's worked at a number of transit ISPs like Level 3, Reach Networks, Hutchinson Global Communications. And he joined Prolexic in 2008, which was acquired by Akamai in 2014. And that's where he is currently as a principal network security engineer. He's also pursuing a part-time PhD at the Hong Kong Polytechnic University, focusing on internet measurement and DDoS detection. And he's going to talk to us about analyzing internet background radiation.
Thanks for your introduction. So, good evening. My name is Akutran. So today I'm going to present our work titled Analyzing Internet Background Radiation with Refractive Telescope. This work is in collaboration with between Hong Kong Polytechnic University and CADR at UC San Diego. So to begin, let me define what we mean by internet background radiation, or IBR. So IBR refers to when packet sends to destination that didn't request or expect them. That's include or the backscatter, the spoof DDoS attack traffic, or some scanning complaint, or misconfigured or expired traffic. So traditionally, the legwork, traditionally the researcher observe the IBL by using the legwork telescope, or often call it darknets. Sorry. So there's some limitation about the legwork telescope. Firstly, it needs a lot of IP address, because the darknets is actually a box of unused IP space set aside for passive packet monitoring. So some of the sophisticated actors, they already know the address space. So they're trying to avoid sending packets to those darknet prefix. Also, for the darknet, it's good to detect global scan, but if the attacker is trying to do a localized or target scan, the darknet is not able to detect those activities. Because there's no interaction between the darknet, so there's no context. For the some of the attacker, if they don't see any response, they will stop scanning the legwork. So it's difficult to understand what their actual intent or their follow-up behavior. So to address the traditional or darknet limitation, so we propose an alternative solution, the refractive telescope. So for the when the prod packet is sent to the production network host, if they don't expect the packet, they will respond with the ICMP error message. So inside the ICMP message, we can recover the original packets. And based on the original packets, we know where it goes, who sent the packet, and why it caused the failure. Yeah. So actually, the refractive telescope solves some of the limitation of the traditional telescope, because there's no need to have the IP address. Is on an active network, And also, there's no need to advertise which address space we are monitoring. There's no hints for the attacker. Because we are monitoring an active network, so we are able to see a local activities. And also for active network, because it will interact with the scanner. So we expect more different level or different stage of scan activities we can capture by using the refractive telescope. And also the last one, because for the distributed refraction dogs attack, the attacker actually spoofed the victim's IP and send packets to the refractors. After sending the first packet, the traffic is only between the refractors and the victim IP. So basically, for the darknet, is completely bypassed. But in our refractive telescope, we are able to capture those real IP address. So basically, our refractive telescope can monitor the type 3 code 0. So it's generated by the router. When the router receives the packet, but is not able to find a route, then it will generate the type 3 code 0. So for the type 3 code 1 is also generated by the router. The router knows the network, but is not able to reach the destination host. For example, is missing the app resolution, then it will generate the host unreachable. For the type 11 code 0, is also generated by the router. So when the packet maybe loop in the network or transfers too many hops, then the TTL expire, the router generate the type 11 code 0. So for the last one, type 3 code 0, when the port sent to end host and the port is not open, then the end host will generate the type 3 code 0 packet. So in our refractive telescope, we define two different telescope. For the RF T3, we actually capture the ICMP type 3 network unreachable packets. For the ICMP type 11, we capture the RF T11 for the ICMP type 11 code 1. So there's other types of code and type pairs, but because they rarely exist in the modern network, so we simply exclude those packets. So for the capability to detect refraction DOS attack, the attacker will spoof the source address of the victim and send packet to the refractor. Because the victim didn't request for the packet, then it will simply generate the ICMP error message. Then because of that, we can capture the ICMP message and see the refraction attack. So we performed the experiment in a transit ISP network in Asia. For the RFTF, T3, we are capture around 1 month of traffic. For the RFT11, we only capture around 7 days. So we are able to capture 14 millions of IP address. Yeah. So during the our data collection, we see our active attack in the ISP network. So in the yellow area, you can see that after March 2023, we see multiple bursts of traffic in our FT3. Yep. The blue line actually showing the RFT3 traffic profiles. For the RFT11, because we start capturing the traffic after March 26, we are still able to see some of the traffic surge during that period of time. It's a challenge because for the IBRO, it's not only attack or scan traffic. It also includes some of the benign measurement. So we need to see not only the active and suspicious malicious behavior IP address. So we're trying to set up 2 steps. Firstly, we just filter out low activity IP address, and then we classify what's their intention, what they're going to do. So for the filtering and selection suspicious source, actually we have 3 metrics. The first one is the total numbers of packets and the numbers of bursts in 1 minute and numbers of bursts in 10 minutes. So for the RFT3, based on this filtering threshold, we can identify 7.1 IP address that is suspicious. For the RFT11, we are able to identify 7.9. Yeah. So
Hey,
after
Echo,
we filter,
just a quick time check.
okay. So after we filter the packet, we're trying to identify what they are going to do. So basically, we just want to see whether they are backscatter or scanning traffic. Yep. So here is the methodology. We are using the port number to determine whether the host is trying to scan or backscatter traffic. So in conclusion, we set up the refractive telescope. We deploy 2 types of telescope in the ISP network. We are able to monitor, we are able to capture 14 million source IP address. And for the RFT3, we also able to capture 38,000 IP address. Okay. Thank you.
Yeah, go ahead.
Marwan Fayed, Cloudflare. So, this is I think it's a really nice idea. One thing that might be worth asking the wider community is, should we somehow open source this or share sources of information, right? Like if you're effectively mirroring these bad packets so that you can inspect them out of band, and it seems to me that this would be, I don't want everybody to have to reproduce this everywhere. I feel like there's a better way for us to collate some of the data that you're gathering and then inspect it together, understand it. Might be worth thinking about.
So you mean where we capture the traffic, or
Well, you're capturing the ICMP information, right? From actors around the plant and inspecting it out of band.
yeah.
It would be lovely if not everybody had to reproduce this in order for it to be, in order to, right? So it's like, is there something the IETF could do, or even the IRTF could start thinking about, is like, is there a way to do this so that we all can benefit?
I think this solution is best for transit ISP or some small ISP. So they have a network. They need to serve some of the customer. Yeah. So basically, for some of their customer, it's not possible to ask them to implement an IDS for everyone. Sure. Yeah. So we need to think about an alternative that is easy for ISP to monitor the network. Right.
Mohammed?
Thank you. I have a very simple question. I would like just to know uh, what do you use the term radiation for this problem, which is so
You mean the application of this solution?
scaring.
Yeah, because scaling. You mean?
Sorry,
What do you mean? Or
that's so scary to this radiation word. You use the term radiation in the presentation.
sorry, can you say again?
Where does the word radiation come from? Is that the question?
Radiation mean you mean the IBR, right?
Yeah,
Yeah.
radiation.
The
Why
background
using
radiation
this
means
term and not why not another more
yeah.
more
Yeah, just like the traditional solution for the network telescope, when you set a set of unused IP address, you expect to see some background radiation. The traffic is subspecies because actually the IP address is not in use, but you're still able to see some of the traffic, right? So what we think about the traffic, some of them are trying to do scanning, right? And some of them trying to use your IP address to launch the DOS attack. So they spoof your address, launch attack, and the return traffic, we call it backscatter traffic. And also maybe there's some misconfiguration in the network that generate traffic to me. I mean, generate traffic to the network telescope. Suppose we shouldn't receive any packets. Okay.
okay and I may understand. I may understand there is a semantic links between what you tackling in the internet and the radiation in the physics uh, semantic of the words. And my question was, why did you pick this?
ACMP.
Why did you choose this word, radiation, and why not another?
Yeah, let's take this
We
discussion
already
offline,
we
maybe.
already want a world without nuclear weapons. They
Yeah.
are not so smart. But that's another.
I think it's
Yeah.
good. Maybe we can take this
Yeah, let's
discussion
take-
offline. Now I
take it
can answer
offline.
your question again.
There's also one question for you in the chat. So take a look at the Meet Techo chat.
Okay, great. And we have still one session to go for more papers. So we're now moving to the last session on security. And our first speaker will be Bolaji Gepedemusi. She's a PhD student at Cal State University working on eBPF and security. Your slides are coming up.
Good evening, everyone. Thanks, Anna, for the introduction. So today I'll be presenting our paper on secure deployment of eBPF programs made manifest. So let's look at the motivation. What brought about this idea? eBPF has unlocked a deep level of control and visibility in the Linux kernel. eBPF is now being used in various environments for networking, for observability, for performance monitoring, and even for enhanced security control. But deploying eBPF, especially in security critical environments, is far from trivial because eBPF runs inside the kernel with deep privileges, of course, and any bug or misconfiguration can crash the entire system, which is not what we want. So the tools that we rely on for security, specifically the eBPF verifier, is not designed to enforce high-level policy, to track provenance, or even to prove code integrity. So the question now is, how do we make eBPF deployment safer without losing its flexibility? But before I continue with my approach, I will just give a brief recap on what eBPF is. So eBPF is a technology that enables us to dynamically extend the functionality of the Linux kernel without modifying the kernel source code and without writing Linux kernel module. So if you want to check more on what eBPF is, you can just check the link below. And how does eBPF work? I'll just run through this briefly. So it starts with a developer who writes a code, either in C, in Rust now, compiles it into a bytecode, and at the same time, decides on the attached points in the kernel that the program will be hooked to. When this is done, the program is passed to the kernel. Before the program can be loaded in the kernel, it is checked by the verifier to know if the program is safe to run. The verifier checks for safety to ensure that the program cannot crash the kernel. It does not run outside the band of the memory, and it does a whole lot of checks. So when this is done, and the verifier passes the program is now ready to be attached to this predefined hook. So if this is done, then it's loaded into the kernel. So we have eBPF helpers that can be used to interact with kernel resources, and eBPF also use maps to share data between user space and kernel space. So eBPF is powerful, but it comes with a lot of challenges. So from this slide, we can see that eBPF is being used in, this is just a lot of places today. But so the ecosystem is really growing. But even with all this growth, there are still a lot of challenges holding back wider adoption, especially in security critical environments. So I'll be looking at some of the challenges. We've identified several challenges, but for the sake of this discussion, I'll just mention 3. So while the eBPF verifier checks for safety, the verifier itself is not foolproof. There has been a lot of vulnerabilities that have been identified in the verifier itself over time. And there is no standardized way to verify where the program came from or whether it has been tampered with. So it is very difficult to make an informed decision whether to trust the program or allow it. And lastly, there is no built-in logging to track what the program is meant to do, and even when it was loaded. So different systems often, add their own tools to track and verify this, which is not what we want. So to address these challenges, we are proposing a framework to securely deploy eBPF programs using manifests and signed bytecode, identity verification, and just to ensure that the program is compliant, and as well, the program is traceable and accountable. So here is a overview of our proposed framework. So I will quickly go through this. So, so we are proposing that, okay, when a bytecode is written, then, when the program is written, the bytecode is generated, and a manifest is generated over the bytecode. So the bytecode is then signed. So when the bytecode is signed, the bytecode and the manifests together will be combined, and a hash should be computed over it and sent to the transparency log. So when this is done, the transparency log returns the proof. So the program can be packaged together, sent to the loader. So the loader is like the gatekeeper before the kernel now. So the loader now checks for some policies that have been defined by the organization to see if the program is allowed to pass. So if the program allows the program, if the loader allows the program can now be passed to the kernel. So the kernel will do its own check. Like that's when the EBPF verify that I mentioned earlier can now come in. So I'll be looking at this in details in the next slides. So let's zoom over the manifest. So what is the manifest? So manifest is like a file, a structured file that declares what the program is meant to do. So rather than relying on informal documentation, so we have a manifest that is both human readable, machine readable, and at the same time can enforce policy. So, so what does the manifest contain? So it has the metadata, the name, the author, the description, just a brief description. This is good for human review and probably traceability later. Then we have the attach rules where the program can attach to in the kernel. So while everything is in the bytecode, but the manifest makes us to abstract, all this high level security stuff out from the code. So then we have the permission. So this talks about the permission that are required for the program to run, like maybe the helpers that are allowed to run, and the system requirements, the kernel dependencies, and the likes. And we have, let's take a look at the trust itself. So to build trust, we need two things. We need integrity, and at the same time, to ensure that the code has not been altered since it was written. So like I mentioned earlier, we have the combined byte manifest that was generated from the code, and the byte code. So now a hash is computed over the two, but before it can be signed, the identity needs to be verified. So this is sent to an identity provider, maybe a certificate authority. So when this is on, the certificate is issued. So when the certificate is issued, the code can now be sent together with the packaging to the transparency log. So this is very important because now nobody can just write any code and send it to the kernel or something without being traceable. So because the code is now logged, so the code can be traceable, and the transparency log as well returns with a log proof, which will eventually be checked at load time before the program goes into the kernel. So yeah, so at load time, so like I mentioned earlier, we have a loader. So and I also talked about the package. So what we have in the package is the signed byte code, the manifest file, and the proof of the log. Like this is public, so it can be traceable. So and we also have the policy. So the policy can be defined by different organizations, but we'll look at the way of standardizing it later. So the loader checks. So before the program can be allowed, to go through the second phase of the verification check, that's the EBPF verifier check. So the loader checks the code. It checks that it has a log proof. It checks, it compares the manifest with the policy. So the policy can be a lot of things. Like I said, this can be the kind of hooks that is being allowed, the kind of helpers allowed, the signers, the capabilities. So if the loader passes this, then the program can now be sent to the kernel so that other verifier check can be checked. And if it's rejected, then that is so this gives us like an additional layer of verification. So now we know who wrote the program, we know what the program is meant to do, and we can be sure that it has not been altered with. So in conclusion, so this is just another level of verification. Normally, the EBPF verifier, what it does is it verifies at load time. So we are looking at a way whereby even before it gets to the verifier, the code is being checked. So now we are looking at adding a manifest to declare the intent. to be sure that the code has not been altered with. At the same time, a loader that enforces policy at load time, so before it gets to the kernel at all. So in the future, when we wrote this paper, so we had an example of this framework, but we aim to implement it, and we started that already, to implement it in, in real world. Then we hope to standardize the manifest format and policy language for interoperability. Then probably later we'll support full pipelines like BCC that people often use, like to write and deploy BPF programs. So thank you. If you want more questions or suggestion, you can contact me via this email.
Thank you, Balaji. Let's see if we have any questions. So let me ask a bit of a clarifying question. So this process happens before the verifier. Is there any interaction here if the manifest, for instance, limits the scope of what the program does, what the intent is? Is this something that would also be used by the verifier, or these are separate components?
Yeah, so this is separate. So what happened in the eBPF verifier earlier on happens in the kernel space at load time, but this is happening in user space. So actually, we have in our paper, we wrote that this can also happen in the kernel, though that we had a lot of complexity, but that is something we will look at as well. But for now, it's in the user space, and it doesn't affect, it doesn't stop the verifier from doing what it's meant to do. So it's just like another level before load time.
Okay, thank you, Balaji.
Okay, thank you.
Okay, so our next speaker is Luis Navarre. He's a PhD student at the UCLA, and his research focus on transport layer protocols, particularly QUIC, as well as reconsidering multicast communication. So please.
Perfect. Thank you. Okay. So I'm a PhD student. As part of my job, I have to read RFCs because I'm working on QUIC. And it's a long RFC, so I have to read it quite often. And once I came across something quite interesting in this RFC. And it's related to section 21.4. It says something about the optimistic attack and that an endpoint may decide to skip packet numbers. So first, we'll review what is a packet number in QUIC, and of course, then what is the optimistic attack. So just to give a quick reminder to everyone, QUIC is a modern transport protocol already serving most of HTTP requests, at least in Europe. It embeds directly TLS inside the design. It offers modern mechanisms such as stream multiplexing and datagrams. And what is interesting in QUIC is that QUIC packets can be viewed as frame containers. So whenever I have to send data, for example, here I'm sending data to a server, I will generate a QUIC packet. And this packet will be identified by a monotonically increasing packet number. So here, the number 1 in green. And this packet will carry frames, for example, here, the stream data that we want to send. When I send a new packet, I will create a new packet with a new packet number. If at some point a packet is lost, we don't retransmit the packet. Instead, we create a new one with an increased packet number, and we will retransmit the lost data. So that's it for the packet numbers. Now, the optimistic attack, what is it? So in a nutshell, we are doing this attack when we are sending acknowledgements for data, for packets in this case, that we don't have, that we didn't have received yet. So we have the following hypothesis here for this presentation. We consider a server to client flow. We control the client, so we are malicious here. And we assume that the server uses a loss-based congestion control algorithm, such as Cubic, for example. So here the server will send some data to the client. the client will acknowledge this data. So the server will say, oh, that's great. I can increase my congestion window and send more packets. The client can acknowledge all the data. And once again, the server will increase its congestion window. Now let us consider that because of this new increase, we generate congestion in the lots. We generate congestion, and so we have losses in the network. By sending these optimistic acknowledgements, the client will say, no, I received everything, don't worry. And so what will do the server? It will say, oh, okay, I can further increase my congestion window. And then at some point, maybe I will saturate my network or the internet at some point. So that's it for the optimistic hack. And RFC 9000 decided to add a sentence to avoid this attack. And for this, they say, we can decide to skip some packet numbers and detect the OAK attack. So yes, if we come back to the previous example, now we skip packet number 9 and directly go to packet number 10. What will happen? When the client says, oh, I received everything for the next flight, the server will say, yes, but I did never send packet number 9, so you're just doing something wrong. So I can close the connection because you are attacking me. So that's it, basically, the idea of this section in RFC 9000. But how well is this implemented in practice? So for this, we took the 16 available server quick implementations from the Quick Interopener, which is an open source project to make interoperability tests between different quick stacks. And we found that out of these 16 implementations, 11 of them do not skip packet numbers, meaning that they are, at least theoretically, vulnerable to the attack. Now that we identified them, of course, we want to attack them. So for this, we use single machine virtual testbed to be sure that we don't do real stuff on the internet. And we leverage these Docker images from the interopener. As you can see on the figure, we limit the bandwidth between the middle node and the client to 5 Mbps. And we measure the transmission bitrate of the server at its egress before the bandwidth limit. Of course, in the first example, it was easy to guess the packet numbers in flight, but in practice, we had to design a predictor to be able to predict the acknowledgement to send to the server. And we came up with something quite easy to understand. So we will, each time we receive a new packet, we will acknowledge D more packets in advance, and we keep increasing the value of D to keep increasing the server's bitrate more and more. So for example, here, when we receive packet number 1, we will say, okay, we acknowledge packet number 1 plus D, so we will acknowledge directly 1 and 2, and we increase the value of D plus 3. It's just an example. When we receive packet number 2, we acknowledge 2 plus D, so we acknowledge 2 until 6, and we increase further by 3 the value of D. And we repeat this process, and so when we receive packet number 4, at the end, we have already acknowledged packets until 14. So that's it for the results. So basically what we can see from the picture is that we can attack all the 11 server implementations, meaning that we can force the server into sending more data than they should with the 11 implementations. For example, with MS Quick, we could reach more than 1.5 gigabits per second. Remember that we had a 5 Mbps bandwidth limit. With Nginx, it was more than 2 gigabits per second. And with XQuake, more than 100 megabits per second for almost a minute. Sorry. What is also interesting with this attack in Quick is that the contents of Quick packets are end-to-end encrypted. So the only person that is capable of reading the acknowledgements is the server. A middle box cannot decrypt the packet and see the acknowledgements to say, oh, you are performing the attack. So the only thing a middle box could do is analyze the traffic pattern of the client. So we decided to measure the traffic pattern that the client, so the throughput that the client is sending to the server. And what we saw on the right is that a client does not send more data to the server when it's performing the attack. So the middle box cannot just say, oh, you are doing the attack, I will block you from the server. Finally, we also wanted to make a real network experiment. And so for this, we had the agreement of a real CDN to do this on their network. So we hosted a website, a website on their CDN, leveraging their network stack, their DOS mechanism, defense mechanism. And as you can see on the figure, we just wanted to be cautious. So we limit the bandwidth towards my laptop to 1 Mbps, and we measure the bandwidth we receive from the network at the A letter just before the bandwidth limit. And basically what we could do was to increase the bandwidth sent by the server to more than 100 megabits per second, despite the 1 Mbps limit, showing that even a real deployed CDN with a real quick stack was vulnerable to the attack. So of course, when we are doing a kind of an attack in a scientific paper, we have to discuss with the maintainers. It was a great opportunity, and we had some great results because some of them decided to directly patch their implementations. So for others, it's still a work in progress. And interestingly, maintainers decided not to do anything because they're not running servers, but only clients. So they said that the space of attack was quite limited. So that's it for the presentation. Just in a nutshell, we were talking about the optimistic attack, so increasing the server's bit rate. IRC 9000 provides a way to avoid this attack, but it was not widely implemented at the time of this work. Again, here we focused on the server to client flow and on a download of a file, but it's independent of the direction and also of the application protocol, so it's quite of a generic attack. Thank you.
Thank you. We have Lucas in the queue.
Hi, Lucas Hagen, Hasselblatt Institute. Yeah, thanks for the great talk. Interesting work. Just for my understanding, if you skip packet numbers in Quick, does that mess with the cumulative ACKs that sort of in a normal scenario the client would have to send back? So you can't just say, okay, I cumulatively ACK the last 100 packets, but if you skip something, then do you have to sort of name that whole in every acknowledgement or only once?
Thank you for the question. So of course, if you skip the packet number, the client will have to create a gap in the ranges of acknowledgement it sends to the server. But you only do this until you get the acknowledgement from the server that your acknowledgement was correctly received. So the client might continue having this hole in the ranges until the server say, oh, okay, I see that you acknowledge my packets, so you can just stop acknowledging these packets. So I would say that it's up to 1 or 2 RTT, the time during which you have this hole. And in practice, we don't have to skip packet numbers that much. So the gaps induced by this protection are not that huge and don't have a full impact on this. Yeah.
Okay, thank you.
Thank you.
Hi, another Lucas Pardew from Cloudflare. I haven't got a question, just a comment, and I'm sorry, but I wanted to say thank you so much for doing this work and reaching out to the different Quick implementations that were affected and going through the responsible disclosure. This goes to anyone, any researchers, like the Quick. This isn't the first bug we found in Quick implementations, not the protocol itself, but variances in how we implement things. It won't be the last. We really appreciate people reaching out. Come and speak to the Quick chairs. For instance, it might be a case where we want to do a collective disclosure kind of thing. This was a bit different, but we got there. We were able to mitigate these issues. This was great in that it wasn't just, oh, you could do this, but that you went the extra efforts to demonstrate that this was like a practical way of doing stuff that makes it really easy for project maintainers to be able to say, oh, this is something we really need to fix, and that they can prioritize getting that done and engage in a dialogue. So yeah, good work, and thank you very much.
Thank you. And just to say that the Quick maintainers are quite nice also, so don't hesitate to reach out to them if you have any bug report.
Sergey Gorinsky from MD Networks Institute. So thank you very much for interesting work. So I didn't read it, but I actually tried to search the proceedings, but it was always hanging on me. So I don't know whether you said it or not, but about 30 years ago was a paper by Stephen Savage on a TCP with misbehaving receiver. So to me, it seems a very similar type of work, because in TCP is essentially there is also accounting done differently. Essentially, you count bytes, and that's what you acknowledge. And essentially, receiver could acknowledge bytes separately, and it's somewhat similar to the attack you described. And I also remember that time, because I did something similar in the context of multicast. I wrote some papers on multicast with misbehaving receivers when they're doing some similar attacks. And also when I was giving a talk and tried to generate excitement about it, I was citing even the companies that try to sell TCP accelerators, how you can download much faster than you're supposed to by doing these tricks on the receiver side. But overall, I think there is not much excitement about the topic, right? It looks like it's not like really there was a TCP specification or implementation which changed. It looks like there is an attack, but I think maybe people thought maybe because it was a kernel solution, maybe there is no, or some other reason. It looks like I didn't really see kind of thorough solutions to the problem.
Thank you. Yes, so it's an old attack, of course. It was initially discussed, yes, in 1999. And what is difficult in TCP, as you said, is that we are counting bytes and not packets. So there were solutions that were suggested for TCP, but they were not implemented because it had to change the design of TCP at some point. So it was quite difficult. And during this work, we were able to discuss with some maintainers of the TCP stack in Linux. And they say that to counter this attack, what they do is they limit the maximum transmission bit rate with a set of opt towards the client. And so they say we don't need to care about this in TCP because, yeah. But at least this attack is theoretically still possible in TCP. And also just to make some publicity, one of my colleagues will be discussing this during TCPM. Extra solutions if you are interested in this for TCP.
Okay, thank you.
Thank you.
Okay, thanks a lot. So let's move on. And our next speaker is Mariam Hadami. She is a PhD candidate in computer science at Concordia University in Canada. And Mariam's research centers on lightweight security, compression, and onboarding mechanisms for constrained IoT devices. So please, Mariam.
So, hello everyone. I'm Mariam. Hello everyone. Thanks for joining. I'm Mariam, and today I'm gonna present my work about a framework for secure autonomic IoT device management in the constraint networks using the CHIC and Brusky. And this work was done as my master thesis at Concordia University under the supervision of Dr. Cespedes and Dr. Atwood. So first I'm going to tell about go through the introduction and then go through the related works, and then present the proposed framework and move to the discussion about the work, the experimental results, and finally the future work of this framework. So as an introduction, you know that the IoT is growing and it's demanding more and more these days. And so we need a scalable and secure onboarding for these networks. And so the current solutions address either constraint or the IP networks, but not the both. They have the solutions for the secure onboarding for just the constraint networks itself or the IP networks. So our solution is to bridge both worlds using CHIC0, which is a context we defined as a CHIC0 inside the static context header compression, which is an RFC defined by the CHIC working group, and using Brusky, which is the bootstrapping remote secure key infrastructure, defined in the Anima working group as for the onboarding, secure onboarding solution in the IP network. And CHIC is gonna make the connection between the actually constraint networks and this non-constraint. So we used LoRaWAN as a case study of the constraint networks to show that this framework is feasible. And our goals is to show the interoperability and the minimal configuration and the security which is available in this framework. So in the related work with the references added, first we checked the works were done in the actually the IP and the non-constraint networks. So we came up with the autonomous networking defined by the ANIMA working group. So it's about self-configuring, self-management networks. So it can help us to reduce the human intervention, and which is defined by the RFC 8993. And inside this working group, they proposed Brusky as RFC 8995 to enable the zero-touch secure onboarding in IP networks, but not constraint. And its goal is to establish virtual out-of-band management plane in a secure and autonomous way without using human intervention. So in the work we're done in IoT onboarding solutions, the existing approaches like LoRaWAN, CoAP, CBOR, which are included in the constraint networks, these are all limited to closed domains. So it means that, for example, in LoRaWAN, as a constraint network, it's like an isolated island that it has the onboarding and security inside itself, and there is no connection with outside of it, like the non-constraint networks. So there was also another draft defined as a constraint Brusky, which is Brusky, which came after Brusky, and it used DTLS and CoAP and some signatures which are more compressed and proper for the constraint networks, but it lacks further compression in the packet headers, or it didn't really check that whether it fits in the MTU, limited MTU of the constraint networks. So here's the research gap, that there isn't a single framework covering the secure, scalable onboarding from these constraint networks to the IP networks. So this is our proposed framework. You can see as an overview, here is the end device, and which is actually comes after, which is followed by the network server, and this is the LoRaWAN network. And then here we can see the IPv6 network, which starts from the proxy and the registrar connected to the validator, which is used here as for the security entity to validate the end device here. So the thing we did is that we defined a CHIC context, named the CHIC0, embedded on the end device, and another, the same thing, on the network server. So we can make sure that the packets are passing from this IPv6 network are able to be passed through these constraint networks. So the header are compressed in this in between. So what we did is that, this framework enables secure onboarding using CHIC rules, and the Brusky itself here is using the validator registrar to actually create a certificate for the end device, and making the TLS tunneling to provide the security in between. And we provided the CHIC0 context to actually compress all the messages required for onboarding the device as defined in Brusky. For example, first we have the Slack, which is actually a method to create an IPv6 address for the constraint device, which was not defined before. And to pass the neighbor solicitation inside this, we need to compress it with CHIC, and also the mFlood to identify the registrar by the proxy in an autonomous way without human intervention, and so on, using the TLS and voucher request and response between the end device and the validator, and finally the EST enrollment, which helps the device to be enrolled to the registrar, and at the end go to the data plane from the control plane to exchange the data. So, and also here the proxy relays the messages to the registrar And in this framework, also we consider that we are using DTLS over UDP, which is recommended because TCP, although is mentioned a theoretical solution, but due to the LoRaWAN constraints, it's better to use a UDP. So here is a table that I provided so you can better see that what exactly CHIC0 is compressing. So here you can see the headers, all the headers types included in the messages, and these are the header fields that can be compressed by CHIC0. And so we did our experimental setup using MATLAB for now to see that how the whole framework, if it's actually feasible to do or not. So the first figure, you can see that these are showing only the header sizes of the messages. And you can see that in the compressed versions, they're all reduced up to 48%. And the bottom chart, you can see that this is actually the whole packet size being compared between different messages between Brusky and Cibruski. So here we applied the framework on both, using both Cibruski and Brusky to see that how they are, which of them would be better. So we can see that constraint Brusky shows often smaller than Brusky message sizes, but not in all. You can see that many messages are showing the same packet size, and the reason is that in those cases the packet headers were similar and the same, but the rest of them were different. And also in some of them we can see that even Cibruski is showing more size, and the reason is that in that case there were some headers that were not at that time yet defined by CHIC to be compressed. For example, COAP was not yet compressed, which is now we have the RFC to compress those messages. And also we did an experimental result on different LoRaWAN settings, like using different spreading factors. And so here I'm just showing the best case and worst cases. So as the best case with the spreading factor 7, which has the most available bandwidth that we can see. So we can see that actually in the no DC, we can see that we can see best results, less than 10 minutes to do the onboarding, the whole onboarding. But with the 1%, we can see that it is actually more than 6 or 7 hours. And in the worst case, we can even see that it comes up to hundreds of hours. And in the no DC duty cycle, we can see that it's much less. So this is just the result that we can see, but we can overly conclude that Cibruski is a better, actually, framework to use in comparison with Brusky for the onboarding. So as for the future work, we will do the implementation on framework on real LoRaWAN hardware instead of the simulations, and we go to the deeper security analysis and performance benchmarking, and we will do extend framework to other non-IP constraint networks such as PPP and LE. And also I want to add that we can just apply more compression mechanisms as the new technologies will come. And thank you.
Thank you. Do we have some questions?
Hello, thank you very much for the presentation. So so I'm Alexander Pelov. I work at the CHIC working group, and I find actually all the results that you have presented extremely interesting. And I think that a lot of them would be very good if you can bring them also to the working group so that they get actually, standardized, because it's a very, very like a very interesting work and great result. So thank you for that. So that's the first thing, and then a question about the time. So in the last results you said that it will take many hours to join the network, like to do the authentication, right?
Yes.
Hundreds of hours. So do you have any suggestions of what could be changed maybe in Cbrowski so that this time is reduced? Or like maybe it's not impossible, right?
Yes, actually that's a great question. So yes, so for the onboarding, we said that since the onboarding is only happening one time, if it's a few hours or few days even, it's fine because we are achieving a framework that connects both different networks and in a secure way. But yes, still this is an issue that hundreds of hours is too much, almost like forever. But we are thinking that probably in Cbrowski we can apply more compression mechanisms, which will come later, or currently the RFCs are coming, like the CHIC in UNCO app, and we apply more compression mechanisms. It would be feasible in the higher DD cycles in the worst case scenario as well.
Okay, thank you, Mariam.